Hello there, welcome back. In the last module, we motivated the concept of functions with some examples from the real world, such as a drug function. In this follow-up module, we're going to look at functions that may arise from a more abstract context, in the sense that they are not necessarily motivated by real-world considerations. Moreover, we're going to examine the common ways in which the F notation is often manipulated in practice. Once again, you should feel free to pause or restart a slide at any time. Alright, let's get started. To motivate abstract functions, let's consider an example. Suppose we stipulate a purely mathematical rule, where for any number x, we square x and then add 3. This gives rise to a function f of x, defined by the formula f of x equals to x squared plus 3. Terminology-wise, this function is an example of what's called a quadratic function, which we'll look at in more detail in days 3 to 4. Here are some sample evaluations for the function. Suppose the input x is 4. Then since the formula states that we square x and add 3 to get the function value, we thus square 4 and add 3. And this gives us 19. Similarly, for the input being negative 2, we get 7. Notice that the third input isn't a number, but an algebraic expression. That doesn't matter, and the procedure remains exactly the same. That is, we square whatever the input is, and then add 3. Therefore, we get x plus h, or squared, plus 3. Now it's your turn. You should pause this module and have a go at the following practice questions. Alright, as with the examples given above, the procedure is to grab the x wherever it occurs in the formula and replace it with the designated inputs. Don't be intimidated if the input is complicated, because the procedure remains exactly the same. At the end, you should simplify your answer if possible. So for the first question, in accordance to the formula, we square the negative 5 and add 3, giving us 28. The input for the second function looks like quite a complicated expression, but remember that the procedure remains exactly the same. So replacing x by the input expression, we get the following. Since this expression can't really be simplified any further, we'll leave it as such. It's important to note that the x in f of x is only really what we call a dummy variable that symbolizes the independent variable of the function, whether it's something simple like the number 4 or something more complicated like an entire algebraic expression. In particular, we didn't really have to use the letter x to represent the independent variable. We could use, say, a or alpha instead. Although x is often preferred by convention, which letter or symbol one uses is ultimately not that important. In other words, the x in f of x is interchangeable. So overall, these three functions, although written differently, are all exactly the same functions. On the topic of naming conventions, just like how it's convenient to refer to your friend Chris rather than Christopher all the time, it's convenient to refer to a function simply as f of x rather than stating out the full formula. However, this can be problematic if there are several functions in the scene. For instance, suppose in a maths question, you're asked to plot the graphs of 3 different functions together on the same plane. Say the functions y equals 2x, y equals 1, and y equals x squared minus 1. Then it would be somewhat unwise to call all 3 functions f of x, since then it wouldn't be clear which function one will be referring to when they speak of the function f of x. So how can we be more specific? Well, a convention universally used entails renaming the f in f of x to be different letters or symbols. For instance, we can name y equals 2x as the function f of x. No problems there. But then we name the function y equals 1 as the function g of x. and we call the third function something else, say h of x. You may be curious and wonder, well, doesn't the f in f of x mean a function of x? Indeed, under this naming tradition, the f in f of x no longer just stands for the word function, but that the f represents a name for the function itself. This convention allows us to assign different names to different functions, which is immensely useful in a situation where there are several functions in the same. Importantly, this convention is universally used throughout mathematics, and it will be a wise idea to become well acquainted with it. To finish off, let's now try to sketch the three functions together on the same plane. Firstly, here's the graph of the function f, which we now specifically know to be the function y equals 2x and not the other two. Here's the graph of the second function g. Both f and g are what are known as linear functions, whose graphs represent straight lines in the plane. We'll look at linear functions in more detail in day 2. Finally, here's the graph of the third function h. H is a quadratic function, whose graph boasts a unique curve shape called a parabola. As a bit of trivia, did you know that the Sydney Harbour Bridge is roughly parabolic in shape? It turns out that bridges adhering to a parabolic design results in maximal structural integrity. Finally, we can now plot all three graphs together on the same plane. Here's a summary of what we've learnt in this module.